Hi everyone, so I received a question here which is past year from 2018 and it's regarding kinetic theory. So let's look at the question first and we solve the question first, then only we come back to look at the question asked by this student over here. Okay, so let's move on to answer the question first. So it says here that the pressure of 1 mole of monoatomic gas of volume 0.02 meter cube in the container is 2 atm, 2 atmosphere. So it's a very jam-packed sentence. So let's dissect it first. So it says the pressure of a 1 mole, so means by N is equals to 1 mole of monoatomic gases. If you see monoatomic, then you know there will be no rotational degree of freedom. It can only have the translational degree of freedom. So the degree of freedom should be 3, which is because of Vx, Vy, and Vz. Okay, of volume 0.02 meter cube. So volume is equals to 0.02 meter cube. In a container is 2 atmosphere. So 2 atm. So 2 atm, if you multiply it 2 times, I usually take 101325, but in actual exam situation, what you need to take is the constant that is in your constant sheet in front of your exam paper. Okay, if I'm not mistaken, your exam sheet, it should be 1.013 times 10 to the power of 5. I'm not sure, it might be 1.01, I'm not sure, but you use what is being written in your constant sheet. Okay, so you have to check it out yourself. So that this answer will be 202650 Pascal. So we have finished discussing the first sentence. Let's continue. The mass of each atom is 3.351 times 10 to the power of negative 23 gram. So this is mass. So mass of one atom is small m, capital M will be molar mass. So this one is per molecule or per atom, so it's small m. And it says here that it's 3.351 times 10 to the power of negative 23 gram. So we do things in physics is usually in SI unit. So you have to change it to kg. Change it to kg, you divide by 1000 or you times 10 to the power of negative 3 into this part. So if you times it, then you know the answer should be 3.351 times 10 to the power of negative 26 kg. Okay, I'm going to remove this part because you don't write in mathematics like this. Okay, just to tell you. Okay, so these are all the information that we get. So the first question is calculate the average translational kinetic energy of each atom of the gas. So it's a common fact that if you see average, right, average translational kinetic energy, it is for one atom or one molecule of gas only. When you see the word average, it should be coupled together with the idea that it's for each atom. If they're asking for the whole gas system's kinetic energy, it should be total translational kinetic energy. Then that one you need to find the total translational kinetic energy of the whole gas system itself. But now it says average. So average is for each atom. Okay, because the idea of average can only work on a per atom basis because each atom have different speed, therefore they have different kinetic energy. Okay, that's the idea. As a system, you can't have an average. Yeah. Okay, so now in A, we are going to find the translational kinetic energy. So we know that for translational kinetic energy, let's write here. It should be average translational kinetic energy, then it should be 3/2 kT. 3 is the degree of freedom that we have here. It's not just the degree of freedom, but when we talk about translational motion, This TR here is translational motion. So translational motion means by you can either move in the X, the Y, or the Z direction for your translational motion. Therefore, the equation should be 3/2 kT. K is the Boltzmann constant, not the spring constant, not the thermal conductivity. This is chapter 13. Okay, so 3/2 Boltzmann constant will be 1.38 times 10 to the power of -23. But now we want temperature, and it seems like we don't have temperature here. So what should we do to get temperature? So to get temperature, we can go for PV equals to nRT. Why can we use PV equals nRT? Because based on the information given, we have P, we have V, we have N. So technically we have PVN, then R is a constant. So definitely you can find T from it. So it's just a matter of substitution. 202,650. Volume will be 0.02. Number of mole will be 1. Your gas constant, universal gas constant, I think is 8.31 in your constant sheet. And temperature. So if you calculate everything, the answer that you should get should be around 487.00 Kelvin. Something like that. Okay. I might be slightly deviated, but it's around 487. Okay, so you get this temperature, you sub back inside to the equation that is unfinished up here. Okay, it's a bad practice to do that way. I should not do that way. I should get temperature first, then only I start calculation. Okay, but I'm middle of recording already, so I might just as well go with it. So if you calculate 3/2 times K times T, all these things together, you get an answer of 1.01 times 10 to the power of -20 joule. Joule because it's an energy, so the unit should be in joule. So that's for A. So what is B? B asks for the internal energy of the gas. Okay, so I just move. Oops, there's a lot of question down there. Okay, so for B, they ask for the internal energy. Internal energy, you know that the formula should be F/2 NKT. So the F here represents the degree of freedom, which we just now say is equals to 3 for monoatomic gas. So this one is the number of gas atoms. Number of gas atoms, how do you find it? We have to find it using the information given, which is 1 mole of monoatomic gas. Then this one should be Boltzmann constant, this one should be temperature, not much problem. So substitution, 3/2, then N. How do we find N? This one, let's just keep it first. Write this here. Then, what should I do? I want to rearrange the equation. So rearrange the equation, then you get 3/2 kT times N. So 3/2 kT is what I obtained from this part A over here. So essentially we can just use 1.01 times 10 to the power of -20 as the answer. Then I bring it down for question B. Then how about the number of molecules? The number of molecules, how should we do it is, we know that it's the number of mole is 1. Then we know each mole you have Avogadro's numbers of molecules. For each mole of gas, you have 6. For each mole of everything, okay? For each mole of everything, you have 6.02 times 10 to the power of 23 atoms. So in that case, it's just, again, you know the number of mole is 1. So you can straightaway just write the Avogadro's number, which is 6.02 times 10 to the power of 23. So if you calculate that, you get an answer of 6.07 times 10 to the power of 3 joule. Okay, the value is around 6068, something like that. Okay, so that's for internal energy. Then the last thing that they ask for is the VRMS value at 27 degrees Celsius. So VRMS at 27 degrees Celsius, how do you find VRMS? It's just the same old formula like last time, 3 kT over small m. Okay, there's another version which is VRMS equals to 3RT over big M. So this one will be molar mass. Both of them will end up with the same answer. So if you are given information about molar mass, then you use this formula over here. But if you are given information on the mass of per molecule, then you use this formula here. It's the same, it's equivalent to each other. It's not like there are two different formula. You can derive from one to another easily. Okay, so we are using this formula here because we have the mass per atom. So it's just substitution. 3 times 1.38 times 10 to the power of negative 23. Then the temperature, they say they ask for 27 degrees Celsius, if I'm not mistaken. Yes, 27 degrees Celsius. So it means by, we want to calculate this, make sure you change it to Kelvin. So change it to Kelvin is 273.15. So divide by mass of one atom. What is the mass of one atom? I believe is given in the question. So I just get from here, use the kg one, not the gram one. Okay, we are doing physics here. Physics, usually everything is in SI unit. So we do it in kg. So 3.351 times 10 to the power of negative 26. So if you do plug into your calculator, you get an answer which is 608.95 meter per second, somewhere around there. Okay, so that's how I solve question A, B, and C. Is it question A, B, C? Yes, it's question A, B, C for this question. So now let's look at what this student asked. This student say, in A, why does the calculation involve only 1 degree of freedom? Okay, if you look at the working here, they follow the first step exactly as ours. So they obtain the same temperature as ours. They use 1.01, but I use 1.101325. That's why there's a little bit of difference. Yes, okay. So the same step for the first step, but after that, when they calculate average translational kinetic energy, they use 1 over kT, which is weird, because that means by the degree of freedom is only 1 only. But when you're talking about gas can move in 3 dimensions, the x dimension, the y dimension, and the z dimension. So I believe this one, okay, you might point me out if I'm wrong, okay, but I believe this should be 3. Okay, so if you change it to 3, right, I believe then the answer here, you need to times 3. And when you times 3, I believe you get the same answer as what we calculated on the left. For B, the student asks, why can't you use U equals to F over 2 nRT? Well, I used U equals to, yes, you can use U equals to F over 2 nRT, U equals to F over 2 nRT. In fact, yes, it's quite easy to do it that way. 3 over 2 times 1 times 8.31 times 487. Okay, now I'm not looking at the answer. I'll just type it into my calculator and see whether you get the same answer or not. So I get 6070.46 joule. Let's look at whether my answer is correct or not. Yes, it's the same thing, 6.07. 6.07 times 10 to the power of 3 is the same answer. Okay, because these two are actually the same formula, just one is in per atom case, this one is in per mole case. You can use anything you like, depends on what information you are given. So for this situation, I believe you can do both. So feel free to choose anyone you like, and not anyone, any formula that you prefer. Okay, so in that case, what do? Well, they are taking the Avogadro constant multiplied by the average translational kinetic energy. I believe our syllabus, when we talk about average, is the pointy bracket. When we talk about translational kinetic energy, translational means there's a TR down there. Kinetic energy means by its K. So I believe this should be the symbol for it. Okay. So it times by the Avogadro constant, Well, the reason is because of this. Okay, I split it, then this one is the pointy bracket average translational kinetic energy. Okay, but this one, because you go over here, then this one become 1, therefore you can take K translational kinetic energy average times the Avogadro number, then you get the answer. So that's how they arrive at this equation actually. Okay, so it's not that they are wrong, it's just that when they get the answer wrong from A, then the B will salah sekali lah. Okay, so that's for B. So I believe if you times 3, you get the same answer also. Oh, 6070.46. Okay, yeah, if you times 3, you get the same answer. This one times 3 is around 6.06. Yes, it's around there lah. Okay, so question B solved. In C, why can't we use 3 kt over m square root? Yes, I use 3 kt over m square root. You are right, no problem, you can do that. In fact, okay, this one you have to praise yourself, because I believe they used the wrong thing here. Okay, the author is being smart by using some sort like a shortcut, but when it's using a shortcut, I think the author sort of forget that the question asks for another temperature. Okay, so let me explain it slightly further. Okay, this 3.35 that they obtain here, they assume that is correct. Assume that is correct. It's the average translational kinetic energy. So yes, this is actually the 3/2 kT from just now. Okay, you assume that is correct. You assume this answer is correct, then it's actually 3/2 kT. So actually half mv Vrms square equals to 3/2 kT. If you move around the equation, you will get 3 kT over m square root equals to Vrms. Okay, so they know the derivation, that's why they can use some the working like this. But the issue is you have the author forgot the fact that this temperature here is corresponding to the temperature which is 487.0 Kelvin, and 487.0 Kelvin is actually 213.85 degrees Celsius. So the thing is, they are being smart in using some sort like a shortcut, but they forgot the fact that they themselves changed the temperature here. So if they change the temperature here, you can't use back value that you obtained from A. What you should do is you should recalculate like what you suggest here using 3 kT over m. Okay, so all your deduction are correct, and that's a very good thing. It shows that you have stable understanding of the topic, and I believe this should be the way of doing it. But if you see any mistake, please correct me as well, because yeah, sometimes I make mistakes as well. So that's it for this question. Thank you very much.